All right, and in our fifth and final talk of this session, we have Mako, who's going to be telling us about choreographic programming with multiple placement.
It didn't. There it is. Good. It scared me. Hello. My name is Mako Bates. My advisor, Joe Neer, at the University of Vermont in the United States, started working on choreographic programming a little over a year ago as a tangent to some cryptography stuff we were doing. We recently formalized a language, 𝐤λsmall, which features multiply located values. So that's what I'm talking about today. I'm going to try and convince you guys of three things, and I think some of them are going to be really easy. So for example, choreographic languages feature located values. It makes total sense for located values to be located in more than one place. Having multiply located values in your language will help with management of knowledge of choice. And then that's all you need. That is a knowledge of choice strategy in and of itself, and it's just as good as other existing knowledge of choice strategies. I'm going to hold on to the asterisk there for a while, but we will get to it. So here's the paper. You can read it on arXiv. It formalizes 𝐤lambda-small, which is a minimalist lambda calculus for choreographies. We prove the normal by simulation and deadlock freedom. Check that out. But making sure we're all on the same page, what's a multiply located value? So located values, either at the term level or at the type level, get annotated with some party who owns them and is guaranteed to know them. Similarly, a multiply located value is annotated by one or more parties who know them. So on the bottom line here, x is an integer. It's 5. There's only one of it. But both Agnes and Carl know x. We can make that a little bit more formal by talking about endpoint projection. So with a singly located value, it's got some party, in this case P2, that it's annotated with, and it will project to itself or not, depending on whether the party to which you're projecting is P2. A multiply located value works the same way, except that it's annotated with a list or a set, PS, and during endpoint projection, you're checking for set membership or list membership instead of equality. So that's how you interpret and represent multiply located values, but then how do they actually arise in computation? So one option is to replace your communication operator with a sharing operator. So x is an integer known to Agnes and Emil. Agnes shares x with Carl. Now x is an integer known to Agnes and Emil and Carl. Our earlier cryptography-focused stuff worked this way. Whether or not it makes sense for a variable to change its type during execution of a program depends on your computational model and the whole rest of your context. So another option is to upgrade from communication to multicast. So again, x is known to Agnes and Emil, but now Agnes is sending as a single action x to Carl and Frida. We bind that computation to y. Y is an integer known to Carl and Frida. That's how 𝐤lambda-small works. It's the simplest system we could put together. But you can combine those. So again, Agnes sends x to Carl and Frida, but now we do set union, and y is an integer known to Agnes and Emil and Carl and Frida. In order for the rest of the language to work out nicely, you're going to need to support subset-based subtyping, which is a good idea. We should do that. But maybe we need to motivate some of this. So what are multiply located values good for? Well, one, knowledge of choice. I'm going to spend the entire rest of the talk talking about that. But they also help improve things in other ways. They make your code a little bit more flexible, because if Agnes and Carl both know y, and something needs to be done with y, then Agnes can do it, and Carl can do it. They also make your code a bit more concise. So on the second to last line of this example here, we have addition of x and y. It doesn't say who does that. X and y are both known to both Agnes and Carl, so Agnes and Carl will both do the addition, and we end up with z is an integer known to Agnes and Carl. When we were writing 𝐤lambda-small, when we wrote we know, I know, you know, we didn't even bother naming this, but then we wanted to include it in the API for multi-core, so we had to give it a name. we ended up with congruent computation because Agnes and Carl aren't just computing in parallel, they're actually computing the same Z. It's more than parallel, it's congruent. I realize I haven't told you guys about multicore yet. Multicore, census polymorphic choreographic programming with multiply located values. So 𝐤λsmall was an abstract lambda calculus about which we have some nice proofs. Multicore is a Haskell library you can use to write software. Roughly speaking, what we did is we rebuilt Hascore, thank you, Gan, implementing the stuff I'm talking about here, pulling out some other tricks so that you can do this stuff in a way that works out nicely in Haskell's type system and have Haskell's type system actually help you with it. And then we took it a step further so we could do census polymorphism. So several languages so far have done location polymorphism, where you have a role that can be fulfilled by different identities in different contexts. If you extend that to sets, where the whole set, including its cardinality, is polymorphic, then the most interesting application of that is applying it to the census, the annotation or the context on a choreography of who's actually present to participate. This lets multicore express choreographies that are polymorphic on the number of participants. However, let's go back to 𝐤lambda_small. So x is an integer known to Agnes and Carl. Agnes can use x, Carl can use x. What can they use it for? Well, they could use it as a branch guard. But as I was talking about with congruent computation, they can use x together, so they can branch together. This is knowledge of choice. Making sure we're all on the same page. In a choreography, you often need to make sure and form some communication so that different parties can follow the same path through control flow. That's the knowledge of choice problem. There's different strategies. I'm going to only talk about 2 others besides this today. I don't think anyone will accuse me of softballing that. They're very good strategies up there. Yeah. So on the left here, we have a select-based choreography. Agnes knows some integer x, and then down at the very bottom, she and Carl may or may not, depending on the value, need to perform some subcomputation on it. But when they get there, it needs to be located at Carl. So the very first thing Agnes does is she sends x to Carl, call his copy y, then she branches. But in order for endpoint projection to work out, in order for this to be well-formed, she also needs to then tell Carl which branch she's in using these select statements. With multiply located values, we don't need to do that. When Agnes sends x to Carl, she knows the result of that computation. We make that explicit by including her as a recipient. There's no extra communication cost overhead for that. But now, they can both branch on y, and either they do it or they don't without any further overhead. So that's how it improves your knowledge of choice management. And that's actually all you need. 𝐤lambda_small doesn't have select statements. There's no merging process during endpoint projection. All well-typed 𝐤lambda_small programs are well-formed. Not everyone here thinks that type systems are the only static analyzer. They're not the only static analyzer. But this is a big deal for library-level implementations especially. So multicore and Hascore, endpoint projection happens at runtime. So if you're throwing errors during endpoint projection, that's a problem. In terms of how you actually use this strategy, well, you just don't inform your peers which branch you took. Instead, you send them the guard before branching. It will often work out that they already have it, or they already have what they need to compute it. Side-by-side comparison, how does a multi-local and multicast paradigm stack up to select and merge? Well, your communications are all data. If I send you something as a branch guard, you now have a piece of data, a value that you can do computations on. Also, if you have knowledge of choice, you can use that as many times as you want in sequential branches. On the flip side, if you're doing merging of your branches, and that's actually doing anything to the resultant code, that means that you have duplicated code. But let's pull in the asterisk from the very beginning. So what was that about? There will be times when you don't want to, or possibly even can't, send the entire branch guard. And also, if you have a deep nesting of branches, you might not want to send all of the branch guards. That's very easy to do in a select and merge paradigm. We're going to look at what it looks like with multiply located values. It's not quite as clean. But an example, so this is an example of sequential branching. We have Alice, Bob, and Carol. In the middle, let response equals. That's Carol acting as a server. She gets a query from Alice, and then she sends the response to Alice and Bob. But before that can happen, Alice and Bob branch together on a shared variable choice to decide whether to use Alice's query or a query that Bob sends her. And then after they get the response back, they have to branch again so that the right party can call the respective handler on that response. But those two branches are on the same variable choice. So whatever communication overhead was involved in creating choice only gets paid once. Sequential branches are free. So predicate transformers. I haven't met 𤤄lsmall or Van de Bos, so hopefully that's the correct pronunciation of their names. They put this forth a couple of years. In their system, when you have a case expression, there's per party branch guards, and then a static analyzer goes through, uses predicate transformers on the semantics of your program to guarantee that all such decisions are made unanimously. It's a great system. It works out to completely subsume the knowledge of choice strategy of 𝐤λsmall, but I'm pretty sure that in terms of expressive power, they're equivalent. So most of the time, any per-party branching is going to just already be congruent. You just wrote it out multiple times. And then the static analysis of 𝐤lsmall is much more lightweight than the predicate transformer system. And you don't have to write things out for each party. There will be cases where the expressions aren't already congruent. I'm pretty sure. I haven't written out proof yet, but I'm pretty sure there will always be a foundation of shared knowledge from which you can build a congruent expression to replace the per-party guards. So focusing on select and merge, it's the multi-local, multicast system is just as good. Specifically, I'm speaking in terms of communication efficiency. How much data do the different parties need to send over the wire to each other in order to accomplish some desired behavior? Now, core lambda is able to express these things called distributed choice types, using which any program you can express in 𝐤lsmall, you can express in core lambda. Let's deal with the asterisks right away. Neither core nor lambda nor 𝐤lsmall are the final word in the paradigms that I'm using them as examples of. So polycore lambda can do location polymorphism. If that can be extended to location set polymorphism in the style of multicore, that's a big deal. I can't suggest how to do that right now, so maybe somebody else can. But is multicast and multilocal just as good? Yes. We have another star, we have a dagger, but yes, it is. If your branches can be merged, then you can reorganize. Then you could also reorganize them into sequential case expressions. Any common behavior on the part of a party who doesn't have knowledge of choice can be expressed in the middle, in between sequential branches. Your select statements are just going to be adding, or well, they're going to be data communication so that you can add parties to the subsequent branches. But there will be cases where in order to write your program optimally in 𝐤lsmall, you have to have dead branches. Also, 𝐤lsmall represents data values in a sort of embedded mini language, which has its limitations. There are certain structures of data that it can't express, so presumably there are subsequent behaviors that it can't express. I don't have an example. So I have tons of time left. We're going to take lots of time on the last example because I want to look at why we get dead branches. I want to solve these problems. I think I know how to solve them. I have some ideas that aren't quite mature. I also kind of suspect that Maxime has already solved them. So let's look at an example of why 𝐤lsmall ends up with dead branches. So this is, I believe, a completely valid 𝐤lsmall program. Yeah, I'm not missing anything. So at the very beginning, Frida has some value. It's either an annoyingly large list or an annoyingly large matrix. Depending which it is, some handler sub-choreography needs to get called on it involving both Frida and Emil. So they're going to have to branch. But Frida does not want to send the entire value because it's too big. So first, she branches to build this variable guard, which is basically just a Boolean encoding whether her value is a left or a right. She sends that, so now Frida and Emil can both branch on guard. We'll assume for the moment that they end up in the left-hand side list. So they're in that branch. They want to call handle list on list. But in order to get a list out of the sum type that Frida has, she has to branch again. We know which branch she's going to end up in. She's going to end up in the left one. But we have to put something on the right-hand side. I put undefined. 𝐤λsmall is a finite language, so you could always put a default of some sort in there. Or you could update the language so that you have partial matching, partial pattern matching. But from an engineering perspective, those are all bad options. We need to do better than this. And it seems like today we're collecting a whole bunch of ideas for how to do better than this. So those are some of the directions that we're going from here. Give your languages multiply located values. They're great. Read the papers. In particular, I'm going to be humble and say, I want you all to read multicore and tell me what I did wrong, because I'm really excited to hear about that. And stay tuned for more.
All right, there is time for a couple of questions.
Thank you for the very nice talk. I'm a little bit curious as to whether you've thought about applications of this to things like consensus at all, where somehow together a group of agents have to compute some value that they all want to agree on. Do you think that that would look a lot like what you have, or would you have to do something extra on top of it in order to actually express the fact that this arose from consensus rather than from just somebody deciding and sending out the message?
So showing that people start with nothing in common and all arrive at the same thing. The honest answer is I don't know, because I haven't opened up consensus protocols to see how they actually work. I know that being able to make them a little bit irrespective of the exact number of participants is going to be helpful, especially like we would love to model dropout, for example. So in that sense, multi-core is a really important step, we think. As for whether or not congruent computation is going to help us with this, honestly, I just don't know what it is that we're trying to do.
Yes, also thanks for the very great talk. Since you talked about multi-core and also multiple values located at multiple locations, have you thought about values located at either a location or a different location? Because that seems like similar to the distributed lattice we had before.
Yeah, so a value located at either a location or another location, nothing we've written right now represents that specifically. What we do have in multi-core is what we're calling faceted values, where Agnes and Frida both know an integer, but it's not necessarily the same integer. And we would like them to be able to do stuff in parallel with that. Combining that with choices, with like an either type or a sum type, would get you the same thing, but whether or not that would be an elegant way of getting the guarantees you want out, maybe not.
Okay, thank you, but multi-core looks very interesting. I'll have a look at that.
All right, let's thank our speaker once more.